So the first half of the class, we discussed how objects in reality, in particular entities that exist in a network of relationships, especially human beings, can be modeled as a graph. And that graph, in terms of data representation, is best represented as adjacency matrix. Okay. Now, by construction or by definition, we already saw different kind of adjacency matrices, right? We have adjacency matrices that is binary. In other words, either there is a connectivity or connection, or there isn't, 0, 1, or a weighted adjacency, in which case the number can be a continuous number representing like a weight, like a percentage. Okay, it could also be negative. It could also be unbounded. It doesn't have to be from 0 and 1. Okay, it can be any numbers. But to begin our discussion, we will focus mostly on a matrix of zeros and one. Okay. Now, with that, you also notice that there are two versions, right? There is a matrix that is completely symmetric. In other words, Ij, if Ij is equal to 1, then Ji is equal to 1. If Ij is equal to 0, then Ji is equal to 0. Okay. So that would be something that's like a network of friends. Yeah. But it could also be asymmetric. So this would be where you know famous actors or actresses, but they don't know you. Okay. So if you are I and the actor is J, then Aij is 1, but Aji is certainly 0. Yeah, fine. So we talk about that example, right? I used the example data from within Mathematica. This is a list of 77 characters in a musical. And if Aij or Aji is equal to 1, that means character I and character J appears together at some point. Yeah, so that's this. Then I can also make up 3 random examples that also has 77 nodes, but the connectivity is directed. But not only that, there are a few connectivities. In other words, a lot of times the I and J do not connect. Okay, so you have this little island. So now, let's see what we can do. We can analyze. Now again, by construction, we know that it's directed or not directed. But what if you are given a data set and you are not given that information? Do you not know if it's symmetric or asymmetric? Well, certainly you can check. Okay. Now, technically, these 2 statements are the same. So if you have adjacency matrix that is symmetric, okay, that is symmetric, that is usually used to represent undirected graph. Okay. Now, it doesn't have to be that way, because you can have directed graph that just happens that every time I points to J, J also points to I. Okay. But most of the time, if it's symmetric, chances are you're talking about a situation that by definition, Aij is equal to Aji. Okay. So this is not a one-to-one condition, but it tends to be like that. Okay. So for example, in this case, we ask if the matrix is symmetric. True. If the matrix, adjacency matrix is symmetric, then we can ask, is the graph directed? So that is a consequence. The same thing. These 2 statements in this case go together, right? Because you have symmetric matrix that's used to construct a graph. The graph is considered to be undirected. Okay. So ask in Mathematica, when you have a Q, that usually signify that this is a question that checks the condition. Okay. So it's not doing anything, it's just asking Q question. Is something that appears to the right, a directed graph? The answer is false. Okay. Now the other one, actually the other three that I created, you know that by construction, I created directed edges. Okay. So likewise, when I ask, is it directed? It's going to obviously give you true. Conversely, if this is directed now, if it's directed, then it definitely cannot be symmetric. Okay? Is it symmetric? False. Okay, all three. So why do I show you this, even though we could visualize? Well, like I said, this is easy to visualize because you only have 77 by 77. Yeah. By the way, we can also visualize. I don't know why we haven't visualized this. So this is a density plot, right? Let's do it for this guy as well. Adjacency matrix random. Adjacency arrow. See that? Not only is it asymmetric, what do I mean by asymmetric? Asymmetric because if you draw a 45-degree line, it's not symmetric, right? In matrix, that 45-degree line goes like this, diagonal line. So diagonal line for the matrix, 45-degree line for the plot. Okay, see, it's not symmetric. Now this one has the same number of connectivities as the musical example, but it's randomly sparse. This one is randomly sparse, but there are less of them. And this is the one that I want to show you. Once it gets to few enough connections, there'll be some people who are lonely, right? Never connects with anyone, right? So that's this guy, right? Now let's see what kind of analysis. Okay, we did this. Now, when I mentioned earlier that you can visualize and you can see that this is all connected. This is all connected. This is not connected, right? There's some floating elements. The word, the command we set for it is connected. So I apply this. Okay. So where are we? Okay. Connected. There it is. Okay. Yeah, I'm just going to list prepend the randomness. These are three graphs, and this is one. So I'm just going to make all four of them so I can look at them together later, right? Likewise, I make adjacency matrix, all four of them. So instead of having one from the musical and three random, I'm just going to have four in the list. Okay, this is just convenient. Okay. Right. Now, I apply this question. Is it connected? Is connected, and I apply to all of them. It's going to be true, false, false. In other words, this is all connected. This is all connected. This is not all connected. So apparently hidden in here somewhere, there's some that are not connected, but we don't see it. Yeah, it's too small, maybe. Yeah, fine. Anyway, it is certainly definitely not connected, because that's what it says. So connected in this case means completely connected. Okay, so think of it as analogous to the DB scan cluster analysis, where you start with one point, you can eventually touch everybody one at a time. Just keep crossing the connectivity, and you connect everyone. Now, this is a question. Connected graph, is the graph connected? That's a Q. But if I want to identify which items from the graph, which characters from the play are connected, I use this connected component. Okay, so for example, if I say connected components and I apply to, let's say, the last guy, let's say the last guy, connectivity graph number 4, the last guy. See, this is what happened. You guys saw this, right? Visualization, we saw that there's a big group here. There's a triplet, there's a pair, and there's a lot of singlet. This is it. This is the big group. 8, 11, 12, 20. So all these characters appear together. 5 and 71 appear together. So that's a pair. There should be a triplet in here somewhere. If it's the same. Or maybe I was thinking it's a triplet. It's actually a pair. Okay. So if I want to find out what's the size of each the size of each the number of islands, not this, okay, I apply the length, so that's it. So there's only one island, so everybody's connected. There are actually 24 islands, not all connected. So, and if you apply count instead of length, okay, so see, there's one that contains just character number 58 and so forth. Okay. So this is sort of like gauging connectivity. Now, why does this matter? For example, in this case, you try to get some statistics about it, but it's statistics that in graph directed form. So imagine that you have 77 clients, potential clients. Okay, you have 77 potential clients. If the 77 potential clients are completely connected, then let's just assume that everybody sends an email, like a marketing email, okay, from whoever they know to the person they know. Okay, if it's completely connected, I only need to send one person, right? Right? So that island is completely connected. So this guy sent to this his friend sent to his friend to their friend, and so forth. Eventually, I reach everybody. All 77 people get the message. But if they are isolated. I can start with this guy, and he sends to his friend, so there's 2. His friend sent to 3 more, so there's 3. But maybe that's it. You just get 5. You don't get all 77 because it's isolated. So connectedness matters a lot. Okay. In this case, it's not the weight of the connectivity, it's whether or not the connectedness is comprehensive. It's completely connected. There's this other thing called acyclic, or it's a property, but I won't talk into it. I won't talk about it right now or on this class. It's more relevant to most graph connection. But I'll just show you an example of what I did. Okay. I create this one example. Basically, identity matrix 4 just creates a matrix of 1, 1, 1, 1, 1, right? I permute it in that order, so it becomes staggered, right? So it becomes this. Instead of 1, 1, 1, 1, 1, I move it to 1 here, 1 here, 1 here, 1 here. Okay. What's nice about this is that by construction, this is the matrix, this is the graph. The graph is directed. Now the word is it acyclic? Acyclic means does not form cycle. Cyclic means cycle. Acyclic means no cycling. In this case, false. Obviously, because it forms cycle. And it forms cycle. This is like if you have information, like in the internet, you say, I send a spam mail and keeps going around and around and around and around. Well, the reason it goes around and around is because that email chain is cyclic. Okay? So eventually just keep going back and forth. On the other hand, I just make up one other graph just to show you that it doesn't. In this case, 1 goes to 1. Now, I haven't drawn this before, so you think it's a little bit weird. But in graph, you can also have connection to yourself. Okay, you have connection to yourself. So in a way, it's like you know yourself. This usually doesn't mean much in a static context, but in a more dynamic context, like sending the message or reminder. You know, you can send yourself a reminder for tomorrow, right? So you can send your information to yourself the next day. Okay, so this kind of self loop does matter sometimes. Anyway, I just want to make the case where in this case, this guy goes to this guy, goes to this guy, goes to this guy, goes to this guy, but doesn't come back. Okay, it's not cyclic. So the question is cyclic graph? Question? True, acyclic. Okay. So that's a bit more subtle. Sparsity, we actually talk about it already. Yeah. Now, in this case, because there aren't that many connectivities, it's represented as a sparse array. So now, this is an interesting thing. Because you notice that this thing has very, very random, right? This is very random connection. Seems like everybody is connected to everybody. But here, there's some kind of like isolation. There's a little bit click. If you think about it, just as you can do cluster analysis, you can cluster analysis in the real space coordinate. Maybe there's something like that here. Something similar to cluster analysis is a concept called community. Okay, and this is something that is quite useful when you try to visualize a small graph. If the graph is big enough, you can't really get much insight from it. But let's say in this case, you have a small graph. So let's see there. See, community plot. See that? So it's the same picture as before, except it shows kind of like this rubber band bracketing around. So this is kind of a click. This is kind of a click. So this is kind of giving a closeness in the community in a network sense. So it's a little bit like cluster analysis, but not relative to coordinate, relative to connectivity instead. This is actually something that's very useful when you talk about, say, for example, marketing campaign kind of thing. But you have to realize that you can't work something like this with 1,000 clients. It has to be like a group of clients or different profile of clients, or maybe high net worth, right? So your portfolio of high net worth clients consists of 150 individuals. Then certainly you can do this sort of thing. Okay. So notice if it's not connected, it's separate. So this is a very good visualization. Okay. Let me show you another example. This one is not, we haven't seen before, but this is from the CG network. I just thought this one looks nice and you should see. This is another example graph network that shows how you relate gene to different kind of disease. Okay, and you can see that, but you can't see what you can't tell what it means because this is basically maybe this indication of a group of disease that is jointly connected to one gene expression or something. Okay. Now, okay. So far in the beginning, okay, go back to beginning. I just told you, right? In the beginning, you have a location in space with respect to your attributes. And I want to say, never mind, forget about your location in space. I want you to define your position relative to your neighbor or your peers, right? Your connectivity. Okay, forget this. I'm going to flood the room so everybody's floating about. So all that matters is that who's holding to whom. Now I'm going to do the opposite. I'm going to say, what if I am given connectivity, right? I'm given connectivity and I want to put you down on two-dimensional space. Why would I do that? Well, first of all, in order to draw the graph, you need that, right? So if you think about it, look at this graph. Look at this graph. This is defined by relationship, purely by relationship. But when I'm going to draw it on a piece of paper, everybody has X and Y coordinate, right? See what I mean? So X and Y coordinate in this case helps you highlight community. But that XY coordinate, is it a real coordinate? Does it mean anything? It's a virtual dimension, right? It's not a real dimension, right? So if I, for example, if I draw an axis here, this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The coordinate of this point is something like 1, 11. What does that mean? Nothing. It's artificial dimension. When have you seen artificial dimension before? Dimensionality reduction. Okay, so this exercise, so this is, in reality, this is kind of floating in a virtual space. All that matters is that the line here is not even the length of the line, doesn't mean anything. This is all 1 and 0. So the short line, long line means exactly the same thing. There's no meaning. There's no spatial meaning. There's no spatial meaning in a direct sense. This is completely abstract. This is relationship, pure relationship. But because I want to draw it, right? I want to draw it on a piece of paper. Somehow I have to sort of like put on a 2D. Okay? That 2D representation, just like in dimensionality reduction analysis we did at unsupervised learning, this is called embedding. I embed the vertex onto two-dimensional representation. Okay? Now, because it's completely meaningless, I can embed it anywhere, anyhow I like. The only requirement is that two nodes don't land on top of each other. Otherwise, you can't see it, right? That's my only criteria. That's only my only criteria. I have connectivity between nodes. This happens in an abstract relationship space. I want to draw the graph. I have to draw it on a piece of paper, so I have to project the node into coordinate, two-dimensional coordinate. The only thing that requires is that A, two nodes don't land on top of each other. Otherwise, you can't see. Okay? And B, now B is aesthetic. Looks nice. Okay? So A is a requirement. Two nodes cannot be on top of each other. So you see that you can identify 77 distinct nodes because they're not on top of each other. That's good enough. Now, does it look nice? Well, that's a matter of aesthetics. Okay? So A, you must not allow the embedding to put two different vertices onto the same coordinate. That's it. That's the only requirement. The other thing is more like it would be nice if they look pretty. Okay? Now, let's quantify what we mean by pretty. Okay? Different people have different sense of beauty. Okay? Some people like organized. Some people like more organic. Some people like to see things in grid. That's why when I visualize this, okay, I can also choose what's called embedding. Okay? Now this is what is like a graph plot option that allows you to visualize things in a different way. Now, this is where interactive visualization comes in. When I give my analysis to the client, I have no idea which representation gives a clear picture in the client. So what I do is I give an interactive display, and the client can choose whatever visualization is best for him or her. Now, first of all, to demonstrate the point, I reduce the size a little bit so that instead of having 7 by 7, I'm just going to do 24 by 24. Okay, just make the community a bit smaller. So I'm going to reduce that. Because it turns out that it's too big. Okay, now this is my embedding. Yeah. One's called automatic. Notice it doesn't have a double quote because the default is automatic, means Mathematica is going to do something that it thinks is pretty. Well, there's this thing, there's this thing, there's this thing. Let's see what it means. This is what it means. Okay. So I'm looking at graph number 1. Okay. Graph number 1. Graph number 1. Graph number 1. Graph number 1 is the musical, right? Music. So this is the same as before, right? This is actor number 1 appears in stage with 2, 5, 6, 7, 8, 9, and 10. Okay. So character 1 and character 2 appear together at one point. So this is the matrix. This is the graph. Now, the layout or embedding, okay, uses automatic criteria. That means I have no idea. Mathematica find what you think makes a nice, clear picture. Okay. But if I want to clarify this picture in the way, the way I think is, if I'm thinking about, okay, in this case, it's not 77, it's 24, okay? 24 characters. Well, how about this? How about I just put 24 characters in a circle and then make a line connecting them if they are appearing in the same scene. So in that case, the embedding is a location that will put all the 24 points, 77, this 24, in a circle. Now, to some people's eyes, this makes a lot of sense to read because right away I say, oh, look, there are 24 and 1 is appearing with a lot, and see what I mean? So this is one way of embedding. Again, the 12 nodes exist in abstract space. All that matters is the connectivity between them. But I have to draw them in 2 dimensions. So I embed that location on this 2 dimension. Now I can do this in 3D, by the way. Yeah. Now, so if this one looks clear to you, well, in some problem, maybe I would want the character to line up in a row, in a grid. So I use grid embedding. So that maybe that's clearer. Okay. So that maybe that makes sense. If I'm a director of this play, I like to talk to this group because they have to appear together in a scene. Then I talk to this group because they have to appear in the scene. So hey, I tell all my character to stand in line and I just go talk to them. So that's kind of like great. Huh? There are many of them, but I'm just making a few. So layer diagram embedding. So that's another way of looking at things. And that's another way of looking at things and so forth. Right? So again, graph embedding in this sense has to achieve one thing. It has to be one thing, and not put the nodes, different nodes on the same location. Otherwise, it blocks the view. That's it. Anything else, any kind of location, it's a matter of aesthetic and clarity. That is the criteria. And that is the criteria. Now, I can give you a spoiler. I give you a spoiler. that criteria, instead of being based on aesthetics, it could be based on other machine learning criteria. And that is the emerging field of graph neural network. That's the field that's only 3 years old. Okay? It just, one of the first paper came out probably like 2017 started to have that. But essentially, the field only started to become mature during COVID. Okay? So 2020, 2021, 2022, which is this year, this is where instead of having this kind of location that reflects some kind of clarity, it's a location that reflects machine learning algorithm. Okay? I don't know if we'll get to that. But certainly you should get to that in a machine learning class. Okay? And this, tomorrow we'll talk about application, and I can show you what we did. You know, in fact, there's this paper here. You just see, this is your TA, by the way. That's your TA. This guy's your TA. Okay. So we did this. We used the connectivity, except the connectivity graph is defined by something called copula and Granger causality. It's not in this class. Doesn't matter. The point is that there is connectivity. Okay, and I can show it like we just saw, circular embedding, or we can show it with the layer embedding. Okay. But this representation has a different meaning. It has a different. It's not that this guy knows that guy. They all market. They're all financial market. So they're not human beings. Okay. So for example, when I say that SP 500 and Thai baht has a line, it doesn't mean that this is a person that knows that person. It means that it has a financial econometric relationship between them. And so this is something that financial economists would know, but not the point is that based on that, we use the centrality analysis. See, that's the word, centrality analysis. And that's the last subject of today, centrality analysis. Yeah. Right. Okay. Before the break, entities, relationship gets modeled as a graph. The graph is recorded on spreadsheet as a square matrix, right? And you can go back and forth between the square matrix, which is technically called adjacency matrix, and the graph, right? After the break, we take the graph, we analyze properties. Now, in application, different things mean different things. So connectedness may mean a lot more in your social network campaign than it does to me. Okay, so you will focus on connectedness. Maybe sparsity means more, because if it's low sparsity, if it's highly sparse, then you have to think of a different way of campaigning. You can't use social network anymore. You have to use broadcasting or something like that. Okay, so all this, the application is up to the application, up to the situation. Now, we have different tools of analyzing, and all this falls under graph theoretic analysis. So it's under graph theory. If you have a friends in math department, there's a full course on graph theory. So acyclic is a property. What else? Sparsity is directedness, all kind of stuff. These are all properties. These are all properties of graph that can be analyzed. And the analysis yields insight into whom you're dealing with. If your client is a network of 150 high net worth individual, and who knows whom and who likes whom or who doesn't like whom or who follows whom on Twitter or whatever, that might be relevant to you. Okay, the application is endless, but it's up to you. Now, the tools above there is based on very traditional mathematics, acyclic. Then we go to this thing called centrality analysis. Centrality analysis is also based on graph theory. However, it's more relevant to modern marketing than it is to traditional mathematics. Okay, so that's why centrality analysis has to be covered in this class, because it's a big class of analysis. You know, in fact, if I didn't tell you anything about acyclic property of graph, it's okay. You're probably not going to use this property very much in your business, but certainly centrality analysis is big. It's a big thing to know. Okay, so I'll give you a little bit of centrality analysis today. Go to the application and so forth. And anyway, what is centrality analysis? Well, in terms of problem, centrality analysis is an algorithm that takes in adjacency matrix and gives you a vector. That vector gives the relative criticality, i.e. centrality of individual vertex. So if you have a network or graph of 77 characters which connected with this, centrality analysis is going to give you relative weighting of which character matters most, basically. Central in this case means like importance, central importance. Okay, so centrality analysis at the most fundamental level is a function. It's a function that takes in adjacency matrix and out a weight vector. Okay, that weight vector assign a degree of importance, centralness, centrality to each individual vertex. Now, let's go to extreme case, because that's easy. Okay. There are 5 people in this network. Yeah, look at the screen. There are 5 people in this network. Let's, for simplicity, let's use symmetric. These two know each other, right? Okay. Who's more important? Who's more important? Nobody. Okay. Actually, in this case, between this guy and this guy, who's more important? Well, think of it in terms of reach. Okay, if this guy dies, what happened? He dies. These people live on. But if this guy dies, what happened? You actually separate 2 islands. So there's some kind of criticality there, right? So I'm not saying that this guy is definitely more important than that guy, but based on this, there should be something about the network architecture, or more properly, the word is topology. That means that somehow this guy matters more than that guy. So, you should, if you're a doctor, you should visit this guy more than that guy, let's say, okay? For the health of the system. Now, let's try something else. Okay. Now, 5 guys with 4 connectivities. Now it's clear, right? Who's more important, right? So based on this star connectivity, this guy holds the key, right? If you kill this guy, everybody's isolated. Okay? So in an extreme case, it's very easy to see, right? It is not who you are, because actually there's nothing, there's no known attribute. I don't know anything about this guy. All I know is that the position in the network makes him more critical than the other 4, right? How do I assign that in mathematics? So basically what I want is a function, okay? Let's say this is this guy 1, 2, 3, 4, 5, right? I have a matrix. Okay, look at the screen. 1, 2, 3, 4, 5. Okay, there's a connectivity, right? 1 is connected to 3, 2, and everything is 0. I want a function that takes this matrix and output a vector. That vector has a high value for number 3, small value for everybody else. That's centrality analysis. Right? That's centrality analysis. It takes adjacency vector and outputs a range vector. That's it. Now, how does it work? Well, just like when you draw a picture of a graph, right? There's a different criteria. Some people like circles, some people like squares, some people like kind of like star-looking thing. There are different criteria. The definition, therefore, is that centrality analysis is not one function. It is an algorithm that produces the weight ranking, weight assignment, or whatever, the judgment, the scoring. You can think of it as a scoring function, weight vector, but it's based on criteria that you give it. So different criteria result in different measure of centrality. One criteria gives you what's called degree centrality. In this class, we are going to cover maybe 3. 1, 2, 3, maybe 4. This one's a bit tricky. Talk about later. So anyway, so all I'm saying is that, okay, let me show you how. Let me show you how. Okay, so these are different criteria. Different criteria. Okay, and I'm just going to jump directly to the result, by the way. Okay, I'm just going to jump directly to the result. Okay. It's a bit tricky to do. Okay. This is a adjacency matrix. This is the graph. Now I can draw it differently. So that's here. Okay, that's not the point. The point is this one. This is sort of like, let's think of it this way. Let's say this is your network of employees. And you are employee number 1. It's so important. It's so important. Obviously, why is he important? Because he's the character that appears in this scene with 2, 5, 6, 7, 8, 9, right? So obviously, this character in this Les Miserables play is going to mean a lot. So you can think of this as a salary or something. Okay? So obviously, I'm going to pay number 1 quite a lot. Number 2, not so much. Number 3, a bit more. 5, 6, 7, 8, 9, 10, 11. All these guys, I pay very simple salary. So in other words, these are different actresses, actor and actresses. This one is really the star of the show. Okay, this is star of the show. Now, this is very simple. How do I make this calculation? The number of connections. Yeah. That's why it's called degree, because degree is just the number of connections. So one has 1, 2, 3, 4, 5, 6, 7. So, okay, well, this is weighted, by the way. So it's 7 to 1. Okay. So this guy have 1, 1, 1, 1. So that's why that makes sense, right? I pay this star more because he appears in a lot of scenes with a lot of other stars, a lot of other characters. So that's called degree centrality. That's like the easiest way to give salary. Okay? However, this is not very good. Let me just go to another one, which is better. Oh, look. This one, even though actor number 1 appears with a lot of other people, somehow it's not holding the narrative. The story is happening here. Story is happening here. It's more critical here. So this guy gets more weight. Okay? So I'm not going to give you the reason why I get this exact number yet, but you can see that at the end of the day, different criteria leads to different pay scale. Okay? In this case, you're saying something like, oh, you know, the story, maybe this is a side story, right? Maybe something happening, it's not the main story, it doesn't matter much. The main story is happening here. So you should pay these actresses a lot of money because they're actually holding the story together. Maybe I apply another criteria and it's sort of like a mix. So it's a little bit like the beginning. And maybe there's another criteria that looks like this. Oh, this criteria is really weird. This criteria says nobody matters except actor number 1, 12, and 24. It's kind of weird. It's kind of weird. Let's just say that I have some kind of hidden criteria. I haven't told you what it is. Your job as an analyst for your problem is not just to produce all of them. Your job is to say, for your problem, which criteria matters. Now, I'm now going to tell you what the criteria means. Okay? First of all, degree centrality. You are paid in proportion to number of connections. That's easiest to explain. Easiest to explain. But it actually is very, technically in mathematics, they call myopic. You know what myopic means? Short-sighted. So it's only looking at immediate connection. It doesn't look at long-term leverage. Okay? So this is not going to mean very much. Now, I'm going to go directly to this guy called eigenvector centrality. Eigenvector centrality is a very elegant method. What it means is this. Instead of just looking one shot, okay, the actress gets more if he or she actually seen with many more actors. That's just one shot. Let's do this. Let's give everybody same importance. Same importance. Same importance. Okay? But every time you appear with your co-actor, you donate part of your importance to your friend. After all, you know, you share it, right? So you just share your money. And likewise, that person will share with you. Okay. And You keep doing this kind of calculation over and over and over until you get some kind of relative importance. So let's say right now you're getting a lot of money. Okay, getting a lot of money. You have little money. And now I consider this you two are together. You would pay a percentage of your money. He would send you percentage of his money. But he actually has little money to give you. You have a lot of money to give. What happens if you keep doing this? You get more money if you appear in the scene with people who have a lot of money. But people who have a lot of money are people, they have a lot of money because they also have appear in scene with people with lots of money. So this is a very clever way of reflecting the saying. It's not how many people you know, it's who you know. Except when you say it's not how many people you know, it's who you know, everybody has an inherently different importance. You know something important, you're done. In this case, you add another sentence. It's not how many people you know, it's who you know. And who you know is important if they know important people. So it becomes a recursive question, right? If you know a lot of people who are famous, you are famous. But why are those people famous? Because they know people who are famous. Why do they know? Why are those people famous? Because they know. So it's a recursive equation. This recursive equation mathematically corresponds to techniques in matrix algebra called eigenvector decomposition, eigenvalue decomposition. You know how that's done? I'll just show you real quick. This is how important you are. Oops, sorry. This is how important you are right now. Okay. So this is all the 24 or 77 character, right? So right now it already has some kind of different level. Okay. This is how important you are, right? And then you give your money to, you see what I mean? This is the same population, give the same money to population. So this kind of reinforce. You keep doing this and you get equation that looks like x is equal to ax. X, ax. This is called eigenvalue system. Why is it called eigenvalue? Anybody speaks German? Eigen means self or same. So instead of y equal to ax, you get x is equal to ax. So this kind of mutually self-reinforcing importance. Yeah, like saying that a celebrity is somebody who's famous for being famous, that sort of thing. So you really don't have to do anything. You just have to know a lot of people who know a lot of people who know a lot of people who know a lot of people. Eventually you become influencer. Okay, that's why this measure, this vector centrality is very much the key to social network analysis. So it's better than degree centrality because it's not just one shot. Okay, so degree centrality would be like count how many friends you have on your network. If you have 1,000 friends, you're better than 500 friends. But in this case, if you know 10 people, 10 people know 1,000,000 people, you are important. So it's recursive. So this is called eigenvector centrality. A version of this, or sort of like improved or advanced version of this called cat centrality. And a particular scheme is called page rank. Why do I mention that? Exactly. When I was a PhD student, I had to do a lot of research. So I use search engine. When I was a PhD student, I used AltaVista as my primary search engine. Soon, Google took over and killed everybody. The reason Google killed everybody is because the algorithm to rank the search result is better. So you ask me if centrality analysis makes money. Well, it's the same thing as saying, did Google make money? Now, obviously, Google has gone on to do many more things. But the reason Google came from nowhere and killed Netscape, AltaVista, all kind of search engine is because when you key in search term for other search engine, it just ranks in a way that didn't make sense. Google ranked it using this kind of eigenvector-ish. Okay, it's some adaptation to it. They call it page rank. Okay, because the guy's name is Page and it's a ranking. Okay, so how does Google rank search result? It says that this page is important because it's pointed to by many pages that themselves are important. Those pages are important because they are pointed to by many pages that are important. So Google used recursive equation. Okay? And that's how Google became Google. And after that, they did a lot more. Finally, so betweenness or degree centrality, that's a little bit naive. Eigenvector, page rank, these are kind of like same family. There's one thing called cats, but I'm not going to cover that. Now, finally, this one is very good. This one is different. This one is more important in logistics. Anybody know what logistic is? Okay, logistic, well, instead of thinking actors, let's think of this. Let's think of all this as transportation hub. I create a definition of centrality this way. For all the travel, okay, so this is all the transportation hub. There are many 24. Okay. Every pair of travel, okay, look at my hand. I'm going to travel from 18, right, to 5. I'm going to travel from 24 to 8. But I'm not going to travel in a way that wastes a lot of gas. So I'm going to use the shortest path. So I take all the pair of travel and I enumerate all the shortest path. And then every time I pass a point, I get $1. Every time I pass that travel past me, I get $1. So betweenness is like a gateway. How often all the path, the shortest path, has to go through me. So in this case, you can see that 3 is not going to be very important because I can go from here to here. I don't have to go to 3 first, right? So no wonder when I go to betweenness centrality, I already did. Oh, sorry. See, you notice in terms of betweenness, 24, 12, 1 means more than anybody. Because basically, you take all the pairing, it's gonna, from here to here, it's gonna pass through these 3 points. The other one you can circumvent. Okay, so 5 only matters if that's your destination. But if 5 is your destination, nobody comes. But 1 and 12 and 24, everybody has to go through that, regardless of what their initial or final destination is. So that's why betweenness matters a lot. Okay, 1, 12, 24. Now the relative weight obviously depends on 12 is in the middle, so chances are everything. So this is how you analyze centrality. Okay? Again, this is extremely important, and it's probably going to be as much important as traditional statistics going on in the future, because all the data you see will exist in graph form. There is an emerging field, and this is beyond this class, of geometric deep learning. It's like that deep learning that you hear so much about, except it's learning on the graph or geometric structure, something like this. So graph is like one of the geometric structure. Okay, and that is the future. That is the future. Now I'm not going to go there. A little bit, even beyond me. But the graph part and the graph embedding, the graph embedding I use. Probably won't teach that in this class, the machine learning based graph embedding. But I give you the paper when it comes out, because it's very important. It's a little bit like this thing gives you some kind of an assignment of importance. Now, what if instead of giving an assignment of importance, you give an assignment of closeness in the abstract graph and do the embedding in that area? It's a little bit like that community plot. You use machine learning. That's called machine learning based graph embedding or graph neural network. And that's the field that only became mature during COVID. Started before COVID. But the algorithm and the research is not that mature. But now it's mature. Okay. Yeah. So I think with that, I'm just going to leave at in the second session and leave time for you to work. Now, what about your project? You're going to do a project, right? Write up. Okay, I'm talking about in terms of deliverable. It's going to be some computer codes, obviously. Okay, but don't just hand in the code. You have to write a paper. What you did, methodology, data, this project. So your TA can go over some details in a workshop setting. So what you want to do, what's your problem? What's your data? What's your methodology? What's your results? Right? Now, the paper and the data visualization, by which I mean, using interactive, like with manipulate, or if you really want to use Python, you can use widget that Gong Gan told you. Okay, so interactive visualization, understand what the data looks like, and so forth, even give some statistical properties. So all the write-up, the data part will account for 40%. Okay, 20% is how you apply unsupervised learning to the data set. 20 more for supervised learning. So that's what, 80, right? The final 20 is, because this is Basai, you will do some kind of video recording presentation. We'll talk about it later. You can see the link from last year, the previous students. They've done plenty of that as an example. So the students of all the previous years, I guess, they would do the project, again, paper, codes, results, analysis, and video presentation. Now, that video presentation doesn't mean you have to do any kind of acting. It could be like you describing and going through the slides. You know what I mean? So it's not, this is not about theater, okay? But the video visualization. So it's not visualization necessarily with Mathematica. That's part of the methodology. But the video, you can record it however you like. For example, when I was using, I wrote like a Mathematica app that predicts COVID, evolution of COVID, trajectory of the COVID contagion. And I use a program called Loom. Loom is like a screen recording. So as I narrate, I move button, all that, and it just records. But I think nowadays you can even use Zoom. I'm not quite sure. Okay. But I think Loom is one thing that's very useful, but you can use anything you like. This is really up to you. It's not. So the 20%, which is about video presentation, the skill of how you produce the video, that's up to you. I'm not really a audio visual person. Okay. So be as creative or not creative as you want. The thing is, you have to show that you understand the problem, clearly define it, clearly explain it. So it's not so much on how exciting the video looks, but how clear your communication is. Yeah. Yeah. Well, I think in a way I'll leave it up to you. Some of the projects are very conceptual. So the coding part may not be a big deal, but some project may be very heavily on coding. For example, because, say you're using a big data set that you have to use a sparse array because the big full array that is too dense, occupies too much memory. You can focus on that. Up to you. Just make it look good. You can sell your ideas. You're clever because your idea is clever. You're clever because you pick an interesting problem. You're clever because you know how to identify the supervised learning task, unsupervised learning task properly. You're clever because the algorithm takes too long and you figure out a shortcut because you use sparse array. Fine. Up to you. Okay. And in a way, this is kind of like a bad side skill. You have to promote what you're good at. Yeah. My job is to even out the skill a little bit so that everybody has basic programming skills. Everybody has conceptual understanding of the topic. Everybody has understanding of why we do this algorithm and that algorithm. But your own strength will be different. Okay. I mean, you can have some guy who said, I'm going to say, oh, this is something that is difficult to do in Python, but I create a library that simplifies it in Python. So it's going, instead of taking 100 lines with my library, it only takes 5. Fine. Okay. Or visualization of data, all kind of stuff. So be creative on 20%. But the first 40%, again, presentation or write-up or visualization, the 40% is to convince me that you are organized, you understand your data. 40% more is about using supervised learning and unsupervised learning to extract insight from data. Okay, so if you look at it and then say, oh, I see from this visualization that A causes B, that's not that 40%. Okay, because if you visualize and get the insight, that's the first 40%. Okay, so let me leave you with that. And the way I suggest you do to make it. Last time I kind of like listening on your presentation. It's not as interactive as I wanted. Okay, it's like, you're telling me a book report. This is what I did, fine. This is what you do, fine. I want, for example, you come up and say, this is my problem. Okay, the rest of you should be contributing. Say, okay, where's the supervised learning element? Where's the unsupervised learning? What kind of data? The 4 things. interval ratio. Okay, is it graph? How do you visualize it? Do you allow the user to visualize different? It shouldn't be. I raised my hand. This is what I did. Okay. It should be you take over the class and then your friends. Yeah, can you guys do that? Okay. Oops, sorry. Oh, I didn't leave you much time, but sorry. I meant to give you a lot more. Okay, so I'm gonna give let me copy this and as a what class is this? 12? Save as class 12. Take away. Okay, Cup, just take a break or whatever you like.